let's talk about derivatives. Yeah. So I know we spent a lot of time last semester talking about derivatives. Hopefully you remember what a derivative is. Even if at like just a baseline level, all walked away last semester from remembering was that a derivative is the slope of a function. Yeah, that's pretty much the gist of it, right? You can visualize it as the slope of a line that's tangent to whatever curve you're talking about. And we spent pretty much the whole semester learning how to do this process called differentiation, where you have a function and you find its derivative. Right? There's a bunch of derivative rules you memorize. Learned about the chain rule and all this other stuff. So today we're going to learn about its opposite, okay, the antiderivative. And this is going to basically set the tone for the rest of the semester, really the rest of calculus. Okay, so you can think of calculus as like a two-part story. Okay, derivatives and then antiderivatives. So this semester we'll focus on the antiderivatives. So let's talk about what that means, right? Yeah, it's definitely, I mean, say it's about the same. Yeah, it's just the other side, or maybe a little bit more challenging, maybe, only because it's newer. Yeah. So let's just review some derivative rules. Yeah, let's try to get back into it. I'm going to give you like 2 minutes here, or we'll see how long it takes, to work out these 6 derivative problems. Just find the derivative, see what you remember, kind of put you on the spot here. And we're differentiating with respect to x, in case you were a little confused about the last one. But yeah, give you about 2 minutes to work out all these, and then see if we agree on the answers and go from there. All right, looks like most everyone's finished at this point. If not, it's okay. See if we agree on these answers here. The derivative of 3x squared. We'll use a little power rule here, right? 2 times 3 is 6, so we get 6x. Good with that? Okay. What about the next one? What's the derivative here? Yep. Negative 8x to the negative 5th power. So you remember the power rule, right? You just subtract 1 from the exponent and then multiply that by the coefficient. This is all old news here. Hopefully you haven't forgotten over the break. Right? When you differentiate a constant, you just get 0. Now, if you have something like this 5th root, sometimes it's easier to rewrite it as an exponent. So this would be like x to the 2/5. Right? So if we differentiate that using the power rule, bring that 2/5 down. 2/5 minus 1 is negative 3/5. So you can leave it like this. Or if you really like writing those radical symbols, you could write it like this. 2 over 5 x to the, or you know what? Let's write it like the 5th root of x cubed. So that would be correct too, although you don't usually need to go that far. Right? And so number 6, we have just the regular old power rule here. Bring that exponent down, multiply by the original coefficient, and then subtract the exponent by 1. Any questions? All right, you guys remember derivatives? Yeah, boring. Yeah, let's get to the more interesting stuff. Let's talk about an antiderivative. All right. So an antiderivative is a function whose derivative is the original function. Let me be a little bit more clear about that. Let's go back to here. Okay, if 6x is your function, then an antiderivative of 6x is 3x squared. Okay, so 6x is the derivative of 3x squared. 3x squared is not the, but an antiderivative of 6x. Yeah? So what we're going to be doing for like this whole semester is going backwards like that. If I give you a derivative, I want you to give me the original function, right? So let's take a look at a couple of examples here. Now I want you to consider these functions, okay? Before we start finding antiderivatives, and there's like a whole list of antiderivative rules that you'll learn just like you learned the derivative rules. Take 30 seconds here and just look at all those equations, and let's consider the derivatives of all these. Yeah, like what's the derivative of y equals x squared plus 3? Yeah, 2x. What's the derivative of x squared plus 2? Yeah, 2x again. They're all 2x. What is that constant doing to the graph?
It's just shifting the y value up or down.
Yeah, it's not affecting the slope of the graph, right? So this is why when we think about antiderivatives, I really want to place a big emphasis here that when I ask you to find a derivative, there's typically one answer. There's a derivative, one derivative, the derivative. But if I give you a derivative or a differential equation and want you to go back and find the original function, I want you to find the antiderivative. There's not just one antiderivative, there are many. If your function is 2x, we can see that 2x has many antiderivatives. X squared plus 3, x squared plus 2, x squared minus, all these are antiderivatives of 2x. So what do they all have in common though? Or like, if we want to say like, if the question is saying something like, find all of the antiderivatives of y equals 2x. So all of the antiderivatives we want to consider like all possibilities, right? Basically every function whose derivative is 2x. That's right. So we can pick basically any constant we want, right? And so the way we would write that is like this: x squared plus some constant c, where c could be anything. It could be any number, any constant. Okay, all these functions have the same derivatives. So 2x has a bunch of antiderivatives, but they can all be written in that form, that x squared plus c. So when you write an antiderivative, you will always stick on a plus c on the end. Now, I'm not sure if you heard Logan earlier, but he kind of made a connection to like why that would be, right? Would we say that again? Like, what is this like constant doing to the function?
And shifting the y value up or down a certain amount.
Right. So like if I have like a parabola, right? So here's like y equals x squared. If I say add 3 to it, all that's going to do is just shift it up 3 units. What is not changing about that graph though? The slope's not changing, right? Like if I look at where x equals 1, the slope here is going to be the same as the slope there. And that's why y equals 2x is an equation that will describe the slope at any point for any equation that's in this form x squared plus whatever. Because if you shift this up or down, it's not changing the slope at the x values. Doing any other kind of transformation will for sure change the slope equation. But just doing a simple vertical shift does not. Okay, so this seems like this won't be that hard, right? Like, okay, so you just work backwards. You know all your derivative rules, just working backwards. But sometimes it's a little bit more challenging than you might think. So let's see if we can come up with some antiderivatives here. So if we have 2x, so find the antiderivative, which is y. We're going to write that like this. Y equals x squared plus c. Okay, that contains all of the antiderivatives for y prime. So try the next one though. Just give yourself 30 seconds and really just think about it. What you don't have to say it out loud or anything. Just write down, go through. You're basically doing the power rule backwards here. See if you can come up with y. And if you're not sure you got it right, just check your answer by differentiating it. Use the power rule on whatever you come up with and see if you get back to 5x squared. All right, so before we say the full answer here, what does the exponent have to be? So let's think about how we do the power rule. Okay, so like if we have something like y equals x to the fifth, what's the derivative of that? 5x to the 4. Right, so when you execute the power rule, the exponent only decreases by 1. So if you're going to work that backwards, the exponent needs to increase by 1. So what's the exponent have to be? 3. And we know we're going to have this plus c on the end. So like the derivative of x cubed, though, is 3x squared. So how do we get from 3 to 5? Yeah, we've got to multiply it by something, right? And so here's kind of the trick for just these power rule antiderivatives. Is I kind of like finding the exponent first because that's much easier. Okay, you just need to add 1, yeah? And then once you figure out what the exponent's supposed to be, you're going to use that exponent to figure out what the coefficient should be. Right? So we started with 5. That's what we had. But what we need to do is multiply this by 3. I'm sorry, 1/3. Now, why would I multiply by 1/3 there?
Because once 3 goes down, it becomes 15, and divide by 3, and it's 5.
Right. If I were to start here and use the power rule to get back to the derivative, I bring down that exponent of 3. Right? And what's 3 times 1/3? 1. And so that will reduce to 1. 1 times 5 is 5.
So
You'll get there.
It's just what's there divided by the exponent.
The new exponent, yeah. Yeah, the bigger one. Yeah.
So just add the exponent plus 1.
So
You're doing like a double changes.
So we'll combine these and write this as 5/3 x cubed plus c. Now let's do an easier one. That might have been too much right off the bat here. Let's do an easier one. We'll come back to that. Okay, let's say y prime is 4. So think about it like this. I'm saying I have a function and its slope is 4. What's the function? Or what is a function, I should say? 4x, right? It has a slope of 4, right? So y here would be 4x, but then I could add any constant, right? Because 4x plus 1, 4x plus 7, all of those would have the same slope. And so that was a little bit easier. Okay, let's do a harder one. Let's go back. Okay. So let me walk you through this process very slowly here, so make sure you got it. Okay, when you find the antiderivative, we're using the power rule backwards, which can be pretty mentally challenging. But where I would suggest you start is with the exponent. Okay, and increment that by 1. So what's negative 4 plus 1?
Negative 3.
Okay, so I'm going to start with the 8. I'm going to increment that by 1. And then in order for the derivative to have a coefficient of 8, when I bring down that negative 3, I've got to cancel it out, right? I just want the 8. So I've got to multiply this by whatever the reciprocal of this exponent is. So what's the reciprocal of negative 3?
1 over negative 3.
Negative 1/3. Okay. That way, if I were to take the derivative of this and bring that negative 3 down here, multiply this by negative 3, negative 3 times negative 1/3 reduces to 1. And then you're just left with the 8. So the trick here with the anti-power rule is to whatever your new exponent is of the original function, like not the y prime, but the y, after you increment by 1, multiply the entire function by the reciprocal of that new exponent. All right, so this would be y equals negative 8/3 x to the negative 3rd power. Oh, hang on. Plus c. Got to remember that plus c. Did I forget it? Nope, I got them on the rest. If you forget the plus c, then you're only giving me one of the antiderivatives, and I want all of them. So you get 1 point out of infinitely many points. All right, let's try this next one. Okay, so this is y prime. I'm giving you the slope, right? The derivative, and now I want its antiderivative. So y equals, I'm going to leave the coefficient alone. I'm not going to mess with that yet, but I'm going to leave a little space, times x to the what power? What if I increment 3 halves? What's 3 halves plus 1? 5 halves, all right? But I need to sort of balance that out, right? Because if I were to differentiate this and I'm bring down that 5 halves, 5 halves times 2 is 5. That's not 2. So I need to multiply by the reciprocal of whatever that new exponent is. So I'm going to multiply this by 2/5. Plus c. And that's your answer. Yeah, we can combine those, probably should, and just get in the habit of multiplying those out. But don't try to do it all at once. Like, I really want to strongly emphasize that this is going to be easier if you don't try to figure out this coefficient all in your head. Just stick with the original coefficient and actually write the reciprocal down and then do the multiplication afterwards. It will be easier. It will be much less mentally taxing. All right, so let's come up with a rule here. Just like we have a power rule, we're going to have an anti-power rule. Okay, so if you have any function, any derivative, any differential that is in this form where a is some coefficient and n is just some constant as well. Then the antiderivative is going to be equal to something times a times x to the n plus 1. Right? I said plus, I wrote minus. We're going to increment 1. But then I also have to remember to multiply this by the reciprocal of that new exponent. So 1 over n plus 1. And then don't forget the plus c. Okay, you have to include the plus c. Make this a little smaller here. You must include the plus c. That's going to be something that's easy to forget. But if you get in the habit of just doing it every time, it'll just become, part of the process. Any questions so far? All right, y'all ready to do some that are a little bit more challenging? All right. Let's take a look at this one. Any ideas how we might start number 13 here?
You simplify it.
Okay, we can simplify. We can multiply these together. So 15x to the 6th plus 21x cubed plus 6x squared. Okay. So I haven't actually found the antiderivative yet. I'm just rewriting the derivative. Yeah. And then we do each one separately. That's right. So now let's find the antiderivative of each one of these terms. Oh, we're just getting started.
Plus c after all of them.
This is day 1.
Wait, do we just put plus c at the end?
At the end, right.
Okay,
even if you have a bunch of constants, they're all just constants anyway. So if you add together a bunch of constants, you're still going to get a constant. Yeah. So the sum of a bunch of constants is still constant. So yeah, you only need 1 plus c on this. You don't need a plus c for each term. All right, so let's see if we can do this. This is going to be y equals 1/7 times 15x to the 7th plus 1/4 times 21x to the 4th plus 1/3 times 6x cubed plus c. So that's it. That's our antiderivative. We are going to clean it up a little bit, but that's essentially your answer. I would get in the habit of it because most of the time these questions are going to be in multiple choice format. So they will be simplified.
Will they ever have to do anything past this?
If on a free response, no, but usually these kinds of questions are just like find the antiderivative. It's going to be multiple choice. So yeah, let's clean this up. And there's not much to do here. 15/7 x to the 7th, 21/4 x to the 4th, 2x cubed plus c. Yeah, got to remember that plus c. Any questions about that one? Okay. So if you've got a product of polynomials, just multiply them together. So that's just one long polynomial. And then you could just execute that anti-power rule over and over again. You can do something kind of similar to number 14. Or anyone need more time to write that down? Do something similar over here on number 14, where instead of like multiplying every term by, like on the last one, we multiplied everything by 3x squared. Here, we could just divide all the terms by 2x cubed before we start trying to find the antiderivative. In other words, we want to try to write this as a polynomial so we can just use that anti-power rule. So G prime, okay, let's see, 4x cubed divided by 4x to the fifth divided by 2x cubed, 2x squared, right, minus 4x, then we have plus 3x to what power? Negative 2. Yeah. So you have 1 minus 3. Okay, so that's the derivative, right? But we're looking for the antiderivative. If that's G prime, we're looking for G. All right, so now we're just going to execute that anti-power rule over and over again. You might be thinking, okay, well, if we got an anti-power rule, do we have an anti-product rule, quotient rule, all the transcendental derivatives? Yeah. We're basically going to redo everything we did last semester, but go in the opposite direction. We're going to undo it all. Yeah.
That's fine.
All right. So here we have 1/3 times 2x cubed minus 1/2 times 4x squared plus negative 2 plus 1 is negative 1. So negative 1 over 1 is just negative 1, but I'll leave it like that, times 3x to the negative first power. Yeah, so now we'll clean it up. 2/3 x cubed minus 2 x squared. Oh, and I forgot my plus c. There we go. Minus 3x to the negative first power. Now that last term might be written as negative 3 over x, but you can leave it like that. How y'all feeling about this so far? Not too bad?
I just realized that we just can't just get rid of like anything that don't have an X on it, and I'm sad about that because it'll come into play, right?
Let's just say that again.
Like on 16, you can't just get rid of the plus 5 because it would equal 0. It would actually be like 5 divided by 2 squared.
Yeah, you can think of that 5 as being like 5x to the 0th power when you're thinking about incrementing. Yeah.
Yeah, but it means you actually have to do stuff with it.
Yeah, you got to actually do something. Yeah. Yep. All right, number 15. First, we're going to rewrite all these roots as rational exponents. So I'm not going to actually find the antiderivative quite yet. I'm just going to rewrite this as 3x to the 1/2 plus 5x to the 5/3. So now I can just go through those steps again. Same steps, right? So f, see, 1/2 plus 1 would be 3/2. What's the reciprocal of 3/2? 2/3. Okay, so this is going to be 2/3 times 3x to the 3/2. Too many fractions. plus,
3/5 times 5x to the 8.
oh, careful. You want to increment first. So, yeah, what's 5/3 plus 1?
8/3.
Yeah, 8/3. Wait, is it 8/3? Yeah, 8/3. So we need to multiply this by what? 3/8. And then have a plus c. All right, so after simplifying here, we're going to get, let's see, 3 divided by 3 is 1, so this is just going to be 2x to the 3/2 plus 15/8 times x to the 8/3 plus c. Now, I'm totally fine if you leave it like this, but if it were a multiple choice question, you might see it written like this. The square root of x cubed here plus 15/8 times the cube root of x to the 8th plus c. Not a big deal. You don't really have to rewrite it like that, but that's how it would look if you rewrote it using radicals.
On multiple choice.
I would say you're probably going to look like this. Yeah. All right, one more, and then we'll talk about one more thing. That's it. We'll go pretty light on the lecture today, first day back. Okay, so last one here. We'll end off with an easy one. What's G? Not sure why it's capitalized, but it's probably just a typo. Just stick with it. All right, so what's the first term going to be? Just 4? 4x squared. Good. Okay, yeah. And I'm actually going to rewrite it as 1/2 times it. I really like, even if you can do it in your head, and after you do enough of these, like you can do that multiplication pretty easily. But especially at the beginning, when you're first getting the hang of this, I think it's worth writing the fraction like this to minimize errors, especially when you start getting rational exponents. Like if your exponent's like 7/3, that can be, you got to remember, okay, 3/7 and trying to do all that multiplication in your head, not really worth it. I think it's easier if you break it down like this, and then just, do it on the next, do the multiplication on the second step. Yeah, so this would just be 5x, right? Plus c. So yeah, we get the 4 that you had mentioned before. There you go. And you can always, the nice thing about these antiderivatives is you can always check to see if you got it right. Like, let's differentiate this and see if we get this, right? Okay, well, derivative here is 8x, derivative here is 5, derivative of constant 0, so we're good to go. Okay, so just kind of sum up here. An antiderivative, okay, is basically the opposite of a derivative. Okay, antiderivative is a function whose derivative is the original function. And there are infinitely many antiderivatives for any one equation, right? If it's differentiable. But what if I wanted a specific one? I might give you some conditions that you have to meet. For instance, let's say this is my differential equation, 6x squared plus 8x minus 2. That's my derivative. But I also want to require that the original function, in this case y, has this point 1, 9 on it.
So you plug them in at the end and solve for c.
That's exactly right. Basically, what we're going to be doing when you find a specific or a particular solution is you actually find which c I'm looking for. So you just go through the same process here. Like if this is dy dx, y would be 1/3 times 6x cubed plus 1/2 times 8x squared minus 2x plus c. And if we do the multiplication there, which works out pretty nicely, so we don't end up with any fractions here, y is 2x cubed plus 4x squared minus 2x plus c. So this is our function y. These are all the antiderivatives that you could possibly have for that differential. But if I need 1, 9 to be a coordinate on that function, I need to figure out what c has to be. So when you find a particular solution, if the directions ever ask you to find a specific or a particular solution to a differential, they're going to give you some coordinate or some information about the original one. You're going to plug that into x and y and figure out what the c is so that you can write the full equation. So I'm going to substitute 1 in for x and 9 in for y. So here's the 9 for y equals 2 times 1 cubed plus 4 times 1 squared minus 2 times 1. So the arithmetic here isn't too bad because of all the ones. So yeah, 9 is 2 plus 4 minus 2 plus c. So 9 is 4 plus c. It's 2 minus 2 is 0. So what's c? Yeah, 5. That's not our final answer. That's just the constant for the particular solution that we're looking for. So we're looking for a specific antiderivative, not just the general form. So now that we have c, we can actually write that specific, or sometimes it's called the particular solution. Y equals 2x cubed plus 4x squared minus 2x plus 5. Any questions about that? Let's do one last example, then we'll be done for today. Number 18, same kind of problem here. Okay, we're going to find the antiderivative and then substitute in this case, 8, 10, and figure out what the c is going to be, and that way we can get our particular solution. All right, so I'm going to rewrite this one as x to the power of negative 2/3, just to make it a little easier to anti-differentiate. So f will be, let's see, negative 2/3 plus 1 is what? 1/3. Okay, 1/3. And then so I need to multiply that by the reciprocal of 1/3. So 3, good. And then plus c. Yeah. Okay, so that's our antiderivative. I'm sorry, that's all of the antiderivatives. But let's find the particular one, the one where f of 8 is 10. In other words, if x is 8, y is 10. So out to the side here, I'm just going to rewrite this as 10 equals 3 times 8 to the 1/3 power plus c. Now, when you're raising something to the 1/3 power, what are you actually doing to it? Like if you're raising something to 1/2 power, what are you doing to it?
Taking the square root.
Taking the square root. So yeah, exactly. So yeah, when you're raising something to 1/2 power, you're taking the square root of it. That's what it means. That's what square root means. So if you're raising something to the 1/3 power, you're taking the cube root of it. So what's the cube root of 8? 2. Yeah. So 3 times. So 10 is 6 plus c. So what's C? It's what? 4, yeah. So f of x is 3x to the 1/3 plus 4. All right, now you know what an antiderivative is.